Hi, I'm Bono. Today we're going to talk about series and parallel circuits, voltage dividers and current dividers. So far we've covered current, voltage, resistance, and Ohm's law. Now we'll use those tools to analyze circuits with multiple resistors. In real circuits, you almost never have just one resistor. There are usually several connected together. The way they're connected falls into two basic types, series and parallel. Once you understand these, circuits suddenly become much more readable. By the end of this video, you'll be able to tell series from parallel at a glance, calculate the combined equivalent resistance, and understand how voltage and current split across each resistor, the voltage divider and current divider, so you can work through a real circuit problem step by step. None of the math here is difficult. Take it one step at a time and it will all click. Let's get started. Let's start with the two basic ways to connect resistors. Series means resistors are chained end to end in a single line. Current has only one path from start to finish. Parallel means the resistor's ends are lined up and connected to the same 2 points. Current splits into branches. Picture a river. Series is a single river. Water flows along one channel in order. Parallel is a river that splits into branches. Water divides and flows through multiple channels at once. Whether the current has one path or branching paths is the key difference between series and parallel. Each type has one quantity that stays the same everywhere. Series, current is the same through every resistor. Parallel, voltage is the same across every resistor. We'll look at each one in turn. Let's start with series connections. The key property of series is that the same current flows through every resistor. Because there is only one path, current cannot pile up or appear out of nowhere. Whatever flows in must flow through every resistor in sequence and out the other end. So no matter where you measure, the current is the same. Think of a single-lane road. Whether you count cars at the near end or the far end, the same number pass by. There's no other way for them to go. Current in a series circuit works the same way. Voltage, on the other hand, is shared out among the resistors. The source voltage is distributed piece by piece across each one. How voltage divides is exactly what the voltage divider is about. We'll get there soon. For now, just remember, in series, current is shared. Now let's look at parallel connections. The key property of parallel is that every resistor has the same voltage across it. In a parallel circuit, all resistors share the same two endpoints. In a simple parallel circuit connected directly to a source, every resistor is bridged between those same 2 points, so the voltage across each one equals the source voltage. Imagine two waterfalls whose tops and bottoms are at the same heights. Since the start and end elevations match, the voltage is the same for both. Parallel resistors work the same way. The endpoints are level, so every resistor gets the same voltage. Current, meanwhile, splits and flows through each branch separately. All the branch currents add back up to the original total. How current divides is the current divider topic coming up soon. For now, in parallel, voltage is shared. Series shares current, parallel shares voltage. They are exact opposites, which makes them easy to remember together. Now that we know how each connection type behaves, let's calculate the overall resistance of the combination. The single equivalent resistor we get by combining several is called the combined or equivalent resistance. For series, the combined resistance is simply the sum of all the individual values. Two resistors, R equals R1 plus R2. 3 R1 plus R2 plus R3, and so on. For example, 10 ohms and 20 ohms in series give a combined resistance of 30 ohms. Why addition? Series connects resistors end to end, making the path longer and longer. Just like connecting narrow pipes in a straight line, the longer the pipe, the harder it is for water to flow. Each resistor added in series makes the path longer for current, so the total resistance always grows. Series, the more you add, the higher the resistance. Now for parallel combined resistance. This one needs little care, so let's take it slowly. In parallel, combined resistance is not found by adding. Instead, take the reciprocal of each resistor, add those reciprocals, and the result is the reciprocal of the combined resistance in formula form. 1 over R equals 1 over R1 plus 1 over R2 plus and so on. For just two resistors, there is a handy shortcut. Multiply the two values and divide by their sum, product over sum. For example, two 30 ohm resistors in parallel. 30 times 30 divided by 30 plus 30 equals 15 ohms, exactly half. In fact, n identical resistors in parallel give a combined resistance of 1/n of the individual value. 2 give half, 3 give 1/3. The crucial point, adding resistors in parallel always makes the combined resistance smaller than the smallest individual resistor. Parallel adds paths, making it easier for current to flow, like opening extra checkout lanes. More paths means lower resistance. Use the reciprocal sum formula. And remember, the result is always smaller. One note, the product over sum shortcut only works for two resistors at a time. For three or more, combine two first, then combine that result with the next one. The other circuits often mix series and parallel connections, but with the right approach they're manageable. The method is find the innermost group that is clearly all series or all parallel, replace it with its combined resistance, and repeat outward until the whole circuit is one resistor. Think of it like a nested map. Fold the innermost pocket first, then keep folding outward. Don't try to compute the whole thing at once. Take the smallest, clearest group first. One reminder, it doesn't have to be parallel first. Some circuits have a series group on the inside. Just always start with whichever group you can identify most clearly. Also note, some circuits cannot be simplified this way at all. For those you need Kirchhoff's laws, but today we'll focus on the circuits that can be simplified step by step. Now the heart of today's topic. Voltage dividers and current dividers. Voltage divider first. A voltage divider is what happens when series resistors split the source voltage among themselves. We said series carries the same current everywhere. If the same current flows through resistors of different size, Ohm's law, voltage equals current times resistance, tells us the larger resistor drops more voltage. So the source voltage is distributed in proportion to resistance. The formula with R1 and R2 in series and total voltage V. The voltage across R1 is V1 equals V times R1 divided by R1 plus R2. Your own resistor is in the numerator. For example, two equal resistors in series with a 10 volt source each get exactly 5 volts, half of 10. Picture a hose with a narrow section and a wide section carrying the same flow rate. The narrow section, higher resistance, creates a bigger pressure difference across it. That's exactly what a larger resistance does to voltage. Voltage dividers are extremely practical. They let you create any target voltage from a larger supply using just two resistors. Next is the current divider, the exact opposite story from voltage divider. So pay attention to the difference. A current divider is what happens when parallel branches split the total current. We said parallel has the same voltage across every branch. Same voltage with different resistances means, by Ohm's law, the smaller resistor carries more current. Current flows more easily through the lower resistance path. The formula with R1 and R2 in parallel and total current I. The current through R1 is I1 equals I times R2 divided by R1 plus R2. This is the critical point. The numerator is the other resistor R2, not your own R1. Because current splits in inverse proportion to resistance, the branch with the higher opposite resistance gets the larger share of current. Think of two ticket gates. People flow towards the less crowded, lower resistance gate, not the busier one. Now compare voltage divider and current divider side by side. Voltage divider, larger R to a larger voltage, direct proportion. Current divider, larger R to a smaller current, inverse proportion, opposite directions. And in the current divider formula, the other resistor goes in the numerator. That is the most common mistake, so make sure it sticks. Let's put all the tools together and work through a real example. Working it out by hand makes everything click. Example: 10 ohms and 20 ohms in series. Source voltage 9 volts. Solve in order combined resistance first, then total current, then the voltage across each resistor. Combined resistance series, so we add 10 plus 20 equals 30 ohms. Total current Ohm's law, current equals voltage over resistance, so 9 divided by 30 equals 0.3 amperes. Series means this same 0.3 amperes flows through both resistors. Voltage across each the 10 ohm resistor gets 0.3 times 10 equals 3 volts. The 20 ohm resistor gets 0.3 times 20 equals 6 volts. Check 3 plus 6 equals 9 volts back to the source. Using the voltage divider formula directly, 9 times 20 over 30 equals 6 volts. Same answer either way. The order is always combined resistance, total current, individual voltages, and it always works. Here's a practical insight that textbooks and online guides often overlook. Something working engineers actually use. When beginners pick a resistor, they usually look only at the resistance value, but in the field there is a second number you always check, the power rating. That's the maximum wattage the resistor can dissipate as heat before it burns or fails. Common small resistors are rated at 1/4 watt or 1/2 watt. Exceed that rating continuously and the resistor overheats, scorches, or burns out. So what do you do when you need a specific resistance but one resistor can't handle the power? A common trick: use two resistors of twice the value in parallel. Two 2R resistors in parallel give a combined resistance of R, exactly what you needed. But now the power is split evenly between the two, so each one dissipates only half as much heat. Same combined resistance, half the dissipation per part. Parallel isn't only for reducing resistance, it's also used to spread heat and protect components. Always look at the resistor's value and its voltage rating together. That's a skill that sets a designer apart. Time to check your understanding. 3 questions. They will catch you if there are any gaps. Think about each one. Question 1. In a series circuit, the same current flows through every resistor. True or false? Question 2. You connect 10 ohms and 15 ohms in parallel. Which statement about the combined resistance is correct? Choice 1. It is greater than 25 ohms. Choice 2. It is less than 10 ohms. Choice 3. It is exactly 12.5 ohms. Question 3. You connect 10 ohms and 20 ohms in series and apply 9 volts across the combination. What is the voltage across the 20 ohm resistor? Fill in the blank. Have your answers ready? Let's check them on the next page. Here are the answers. Question 1. True. Series has only one current path, so the same current flows through every resistor. Voltage, however, is divided among them. Question 2. Choice 2. Less than 10 ohms. Parallel combined resistance is always smaller than the smallest individual resistor. Let's verify. 10 times 15 divided by 10 plus 15 equals 150 divided by 25 equals 6 ohms. Yes, smaller than 10 ohms. Choice 3, 12.5 ohms, is the result you get if you wrongly add the two values and divide by 2. That's the trap. Question 3, 6 volts. Series combined resistance is 30 ohms. Total current is 9 over 30 equals 0.3 amperes. Voltage across the 20 ohm resistor 0.3 times 20 equals 6 volts. Using the voltage divider formula, 9 times 20 over 30 also gives 6 volts. And the 10 ohm resistor gets 3 volts. They add up to 9 volts. How did you do? Review any you got wrong. The two trickiest spots are parallel combined resistance and the current divider numerator. Keep those in mind. That wraps up our look at series and parallel circuits, voltage dividers and current dividers. Everything today flows from one question: what is shared? Series has one current path, so current is shared. Combined resistance grows by addition, and voltage divides by ratio. That's the voltage divider. Parallel has matched endpoints, so voltage is shared. Combined resistance shrinks by reciprocal sum. and current divides inversely. That's the current divider. Voltage divider and current divider are exact opposites. Bigger R means more voltage, voltage divider direct proportion, but less current divider inverse proportion. In the current divider formula, the other resistor goes in the numerator. Watch that one carefully. For mixed circuits, collapse the innermost clearly identifiable group first, then work outward. The whole topic is one thread. Look at how resistors are connected, ask what is shared, and everything follows from there. Keep that instinct handy. That's all for today. Thanks for watching.